Okay, today we will continue with part number 3 on chapter 4. So currently we are looking at chapter 4 on radio transmission. Okay, so we are looking at the transmission in the radio frequency. Okay, so previously we have seen the first four parts related to transmission. Okay, today we will continue with the part number 5, so which is covering on the impedance matching network. Okay, so there's a term called impedance matching network. So it's a setup of electrical circuit, so which can help you to in your transmission. So why we need this kind of matching network? Because in radio frequency, so there are chances of energy to be lost along the way. So we need to have this kind of setup in order to prevent all these losses. Okay. So RF impedance matching. So why match? So we will look later. Okay, so why is it need some matching? So what goal we try to achieve based on this impedance matching? So we want the maximum power transfer between source and load. A source meaning where the input that you are giving, and load meaning so you the how to say, so the input is source and the output of the system. Okay, so you can see this the output. So in a transmission system, so what is the input? So we already know. So the modulated signal, so signal already modulated, amplified. So that is considered as a source. Okay, so it will be here, and when you are passing through this matching network, so it will ensure that the amount of source you are giving and also the amount of source received is maximum. So that's the goal of this matching network. So meaning here you are giving 100 volt, so you must receive here 100 volt. So that is what we call as a maximum power transfer. So meaning is a successful. So is we do want you are giving 100 volt, but you are only receiving 10 volt. So 90 volt go missing. So we need to have a matching network in order to have the proper transmission. Because when you are transmitting using radio frequency, so we are sending things wirelessly. So if we are using wire, so this thing will be a very minimum because it's wired, so it's connected by wire. But when you are sending in wireless, so you need to make sure whatever things that you are sending must be received in the opposite end. So that's why the goal of impedance matching network is to maximize the power transfer between the source and also the load. Okay, so why? So you can see, so when you have a wireless transmission, so we always will have a transmitter and also receiver. So you are sending the message, it will reach the transmitter. So the transmitter will send wirelessly to the receiver. Receiver will receive, and it will process, and it will go to the end. Okay, so it will give to the end user. Okay, so in the receiver, we want to make sure that no unnecessary losses. Okay, so there can it can be slight losses here and there. So you are sending 100 volt, maybe you are receiving 99.5. So still acceptable. So we want to prevent unnecessary losses. Okay, unnecessary losses meaning so losses that we cannot prevent. Okay, so we need to make sure this. And in the transmitter part, we don't want unwanted reflection, especially high power signal, because when you are sending something, so you don't want and the signal that you are sending to be rejected. uh, so you are sending to transmitter don't want to receive, and is coming back. So that is what we call as a unwanted reflection. So unsuccessful transmission. Okay, so that is what we call as a unwanted reflections. Okay, so this impedance matching is very important because in current situation, so most of the things that we are dealing are related to wireless and also radio frequency transmission. So we need to make sure things are properly encrypted and also decrypted. Okay, so the maximum power transfer for RF circuit. So the maximum power transfer occurs when the load has optimum impedance value. So impedance we always write as Z. Okay, so we want to have a optimum impedance value equal to the complex conjugate of the source impedance. So we write it as ZL and also as ZS. So what is actually is meaning, because you are dealing with alternating current. So alternating current, it has a real value. So in this case is the resistor value. So normally when we see resistor, so it will have a very fixed value. So it will maybe 100 ohm or 1000 ohm. So so we call it as a real part, and we have a imaginary part. So which always will be related to capacitor or inductor. Okay, so it always we write it with the J or I. So I think in mathematics you're already familiar with this. So real part and also imaginary part. So when you are dealing with alternating current, so we are dealing with real part and also imaginary part. So when we want to have a maximum power transfer, so we want to make sure the load, okay, the load L, so must have the optimum impedance, which equals to the conjugate. So meaning the values will must be the same. Okay, so it must be the, okay. So the ZS is this side and ZL is this side. Okay, so it must have a same, because you are transmitting from here to here. So if you are having 100 volt here, you must have 100 volt here. Okay, so it can be further reduced to this kind of for analysis. Okay, so today we will see some kind like mathematics, but I will try to simplify it so that you can understand. Okay, so some notes related to this. So perfect match can only occur in one frequency, resonant frequency. So especially when we are dealing with communications, okay, communication, network communications, so transmitter, receiver. So the we when we are designing the antenna, so we will see the resonant frequency, a term called resonant frequency. So the frequency where the signal is resonating properly. So when at the resonant frequency, so you will have a perfect match, meaning 100%. So that's why when you are designing a antenna, so they always will check. So what is the resonant frequency of the antenna? So based on that, they will make the adjustment. Okay, so the resonant frequency is very important in communication. Okay, at resonance, maximum power transfer occurs between RS and RL at 50% efficiency. Okay, so RS and RL, so it's actually 50% efficiency in the positive side, and negative side is 50%. So its total is 100%. Okay, so you are getting a maximum power transfer. Okay, so at frequencies other than resonance, the match become progressively worse as we go further from the resonant frequency. So resonant frequency is like a peak. Is like a peak. So if you go far from the resonant frequency, let's say the resonant frequency is 1000 hertz. So if you are going far, meaning from 1000 you are going maybe 2000, 3000, 4000, so the signal will become worse and worse. So at the same time, this side, let's say you're moving 800, 500, 100. So if you're moving in a decreasing manner, so it will become worse. So that's why when we are designing an antenna, we want to purchase. We are not designing antenna in mechatronics. So usually it will be in the communication side. But when we want to buy certain components, so make sure, so we check the resonant frequency. So whether the signal that we want to operate and the resonant frequency of the antenna or the circuit is compatible. So if not compatible, let's say you want to send 10,000 hertz, but the resonant frequency of your antenna is only 1 hertz. So we can see thousand hertz and also 10,000 hertz. So as it go further, so we know it will become progressively worse. So we cannot achieve what we want to achieve in the communication. Okay, so it's very important. Okay, so RF impedance matching, why match? So impedance match condition should always be achieved. Okay, so impedance matching. So what we want to achieve using this impedance matching, we want to maximize the power transfer. So meaning you want to transmit a certain value, make sure the receiving end receive the same value. So we want to minimize the signal loss. So we don't want any details to loss in between the transmission. So we want to minimize, and we want to maintain the signal integrity. So you are sending A, make sure the other person receive A, so not receiving B. So that is what we call as a signal integrity. So we want to prevent damage to components, because when we are having different, we are loading a certain components with too much load. Okay, because earlier we have seen, so you have a load, so this is actually a component that is attached to this resistance. So when we are sending more than what it can handle, so it will damage. So that's why we always will know, we will see, so the chip blow, so or the LED blow. So because it cannot withstand the power that we are giving. So it only can manage certain amount of power. So by doing this impedance matching, we want to prevent damage to the component. Okay, and we also have a stabilizing performance. Stabilizing performance mean we want for a certain period of time, so the transmissions are very steady, so everything are going smoothly and is very stable. So we want to achieve that. And how all these five can be achieved is by having a proper impedance matching. Okay, so we will discuss several methods that are related to impedance matching, because there are various way of doing impedance matching. So we will try to check a few methods. So we can have a numerical analysis, we have like L network matching, so we have three element network matching, so pi and also T networks. So we will see in this part 3 and part 4. Then we have a graphical analysis, so use of a Smith chart. We can have software design tools in lab. So usually for antenna design, they will use this CST software. Okay, CST software can be used to estimate the resonant frequency, try to check so how the circuit can function. But in our lecture, so number 2 and number 3 we are not covering. Okay, so we are not covering in chapter 4. Uh, so we're only covering the numerical analysis. So infinitely many ways to do impedance matching. So we can use L or C types. Okay. So we can have all these C, L, all different transformation, meaning the components are arranged in a different way to achieve this kind of circuits. So and we choose the one depending on the application with minimum effort. So, based on our application, for what reason we want to use this impedance matching, so we decide which one is suitable for our application, and we don't want to have like more components added, a lot of components, because when you are working as an engineer, company always will concern about cost. So are you adding? Why you need to add this? So they will be asking why you need to add. So can it be solved using the existing devices or equipment? So we want to choose the one depending on the application with minimum effort. Okay, so impedance matching using L network. So we will see if you networks that are related to this impedance matching. Okay, the first one is the L network, so or we call it as a LC matching. So LC, so L is inductance. Usually induction we call it with the symbol L, and C is the capacitance. Okay, so you can see. So this is like you can see it's like why we call it as a L network, because it's in the L shape. Okay, so L shape. So the arrangement between the inductance and also the capacitor, so will be arranged in a L way. Okay, get parallel combination of capacitor and also load resistor. So we have a load resistor here, so RL, and capacitor is arranged in a parallel way. Okay, so we can do some voltage divisions. Okay, so we can see actually um, this is this is actually parallel to this and also this. So we have three parallel components arranged. So we can rearrange this. So we also can put it this way. Yes. So that's why we have three components here, which are arranged in parallel. And once you replace the values, okay, using the voltage division rule, so we can see that the value we can reduce it into 100 minus J300. Fine. So this for this example. Okay, the circuit becomes like this. Okay, earlier the circuit was like this, J300 and J minus J333 and also RL 1000. So you make it like a L. Okay, so you so 100 is here and this is minus J300 become here. So it become like L network. So once it's in series, so it's easier for you to do calculation. Okay, so the input impedance looking into the matching network becomes so J300 plus 100 minus J300. So once you solve this, so we know that the impedance that we need is 100. So we call it as a RS. Okay, RS. So sorry, we RS equals to RL. Okay, so RS is the source. Okay, the source impedance, see a load of 100 ohm. So this from the previous. So we can get 100 from the as a result. So when we are using 100 ohm in this arrangement, so we can achieve perfect impedance matching. So that is what reason why we are calculating this. So we want to find so how much value we need to include in the current circuit in order to achieve. So because without this impedance corrector or the resistor, so maybe we only can achieve 90% of the transmission. So 10% will become loss. So once you add this into the circuit, then it will become 100% transmitted successfully. Okay. So the system is match and maximum power transfer. Okay. So that is the function of impedance matching. Okay, how does the matching network accomplish this? So there are two setups that we can utilize. One is shunt element. Okay, so all these are for your understanding. Okay, we have a shunt element, so transform large impedance resistance to a smaller value whose real part is equal to the real part of the other terminating impedance. So I will explain later on this. Okay, then we have a series element. Okay, so cancel out resonates the reactive part of the equivalent small impedance. So reactive part means, so we have a real part and also reactive part. So real part is the fixed value and reactive part is the imaginary value. Okay, so shunt element, so you try to deal with the real part, and series element, so you try to deal with the reactive part. Okay, so as I say, it depends on the application that we want to use. So we need to do the analysis, we need to find out what we need to do in order to achieve a perfect impedance matching. So based on that, we can select whether we want to use shunt element or series element. Okay, shunt series transformation. So we also can can transfer. Okay, so shunt, this is a series, okay, because it's connected in the same wire, and this is a shunt. So you have a same input, then you divide into two. Then once it is uh, eh, doing whatever it's supposed to do, it will combine back. Okay, so this circuit we call it as a shunt circuit, and this is a series circuit. Okay, so valid at a single frequency. Okay, so let's say you just want to transmit between one frequency to the same frequency in the receiving end. So we can use this kind of simpler series. So impedance of series leg equal to impedance of shunt leg. Okay, so we can see here. So this is some of the calculation. Okay, how we can expand expand the real part, so which is RS, and imaginary part JXS. Okay, so we have this, so we can further divide into this form, and this form we can expand it to this form. Okay, so there are few things that we can use. Yeah, but we are not using this for calculation. Okay, but we can transform between to series, or vice versa. Okay, so shunt series transformation. So equating the real and imaginary part. So this is for real part. So this formula is already calculated. So once you receive the information, so you just need to replace inside here to find what the value of RS or the missing value. So at times RS is given. So one value like let's say XP is not given. Then you need to replace the values in order to find what is XP. Okay, then and this is the imaginary part. We can calculate using this formula, which can be simplified using the definition of Q. So what is Q? Okay, Q is one important matter in radio transmission. Okay, so we can see why in radio transmission we are using Q. Okay, so if you have taken thermofluid, you know what is the value of Q. So value of Q is actually energy. Okay, we always associate with heat energy, but actually in radio transmission, Q meaning is a quality factor. So Q is quality. So quality means how much energy is stored and how much energy is released. Okay, so we need to have. So if the Q is maximum, so meaning the energy can be stored in a longer period. Okay, similar like our power bank. Okay, let's say your power bank is good. So you charge the power bank, so it become 100. So by not charging, we shouldn't reduce to 80 or 90. So if you are using, it's okay. So Q is actually the same. Quality of how much energy is stored and over how much energy is going out. So if you are putting 100 unit, but under 100 unit is going out without any reason, so that means it's not a good, it's not having a good quality factor. Okay, so let's say you are having money you put in the pocket, immediately the next second the money go missing. That means you're not having a good quality factor. Okay, in terms of financial management. So similar. So in the radio frequency, so Q meaning is a quality factor, or how much the circuit can store energy and also prevent it from dissipated unnecessarily. Okay, so you can use all these formulas to calculate. Okay, so S stand for source, so meaning input to the system, and P. So usually we use P. So P is the power that is transmitted. Okay, so we can use all this. So there are certain formulas that is listed here. so which we can use for our calculation. Okay, so shunt series transformation. So after when you rearrange this, you will get this formula. Okay, so Rp equals to Rs 1 plus Q square and Xp. Okay, so Xp equals to Xs plus times with 1 times Q to power of negative 2. Okay, so this is based on how you rearrange this. Okay, so you can use this one linear formula in order to calculate so whichever value that you want to calculate. Okay, so the L network, so we can see um, so there are two blocks. So one block on the left is actually passes the DC direct current, and on the right hand side it blocks. So you can see so how the components are arranged. Okay, so here you can see. Okay, so first, if Rs more less than RL, so it depends. So later I will show you some example. So Rs is the source resistance, RL is the load resistance. So if the Rs is lesser value than RL, then you use this setup. So if Rs more than RL, then you use this setup. So depending on your equation or the questions asked, then you can determine so which setup you want to use in your circuit. Okay, for impedance matching. Okay, so if you want your circuit to block the direct current and Rs less than RL, then you use this setup. So if you want your circuit to block the direct current by Rs more than RL, then you use this setup. Okay, so you need to determine based on this image. Okay, the quadrants that are given. Okay, so we have more calculations here, more formulas that we can use. Okay, so usually we will ask to calculate Q. We will try to calculate QS, QP. Okay, so it depends on the question. Okay, so later we will see some question for you to get a better understanding. Okay, so example, so you can see here. So this can be like a question that will be asked. Okay, so design a circuit to match 100 ohm source. Source resistance means Rs. So it will be mentioned in the question. To a 1000 ohm load resistor. Load resistance means RL. Okay, so frequency is 100 megahertz. Assume that a DC voltage must also be transferred from source to load. So it's already mentioned here. So you want to pass DC. So because you want to must also transfer. So if the question say assume a DC voltage must not transfer from source to load, then you take this side. So you have to. So it depends on the question, and all elements are ideal. Okay, so from here we know Rs is lesser than RL. Okay, so because Rs is 100, so RL is 1000. So 100 is lesser than 1000. So we need to use shunt element to process across the load. Series element should be inductor, so shunt element should be capacitor. So we can receive. So earlier, so Rs less than RL. So Rs less than RL, and we want to pass DC. So this will be the setup that we will use. Okay, so that's how we determine. Okay, so here you can see. Okay, so inductor and also capacitance. So you can see how it is arranged. So this is the shunt. Okay, so it's like a parallel. Okay, so the matching circuit. So 100 ohm. So you have an inductor. So this is your load. So we need to calculate what's the value of this and this in order to achieve to design the impedance matching circuit. Okay, so Rs is 100, Rp is 1000. So sometimes they will use Rp, sometimes they will use RL. So, but I strongly suggest you to use RL so that you know. So this is source resistant, this is load resistant. So suddenly you use P, then you get confused. What is P? Okay, so here you have QS equals to, okay, so here I change P, you change to L, so QL equals to, so for this you use these formulas. Okay, so you have a few formulas here and also a few formulas here. Okay, so you can determine which formula you want to use. Okay, so here we are using this formula. Okay, RP over RS minus 1, so square root. Okay, so here 1000 divided by 100 minus 1. So 10 minus 1, so 9. 9 square root of 9 is 3. So QS equals to QP equals to 3. Then you can calculate the excess. So excess is, okay, so you can find. So even this formula, excess is QS times with RS. So QS times with RS. So QS we know is 3. So RS we know is 100. So we know the value of XS is 300 ohm. Okay, and XP, so we can also use the same similar formula that we can calculate is 333 ohm. Then we can calculate the imaginary part. So this is the real part. This is the imaginary part. So we can calculate based on the formulas. Okay. So we have all these formulas here. So we can use these formulas to calculate. So XS equals to 477 nano Henry, and XP equals to 4.8 picofarad. Okay, so we already know this. So we can create our impedance matching circuit. Okay, so this is just a simple example for you to understand how we can design an impedance matching circuit. Okay, so dealing with complex source and load impedance. Okay, so earlier we have seen it's a bit like direct because the values are not so big. There are no not many components in between. So we consider this like a very simplified circuit. But how if when we deal with complex source and also load impedance? So we have a different kind of methods that we can employ. So like absorption method. So we can have a resonance method, or we can combine both. So we can have all these three arrangement. Okay, complex load and also source impedances. So previous example, these were real source and also load impedances. So in practice, source and load impedances are complex. So for mathematics, we can do like the previous circuit. Okay, but in the real practice meaning in the real life, source and also load impedances are complex, so are not direct. Okay, so there are two basic approaches to handle complex load and also source impedance. Okay, so we can use the absorption method or we can use a resonance method. So we will see one by one how it can differ. Okay, so absorption method. So stray source or load reactants can be absorbed into the impedance matching network by proper placement of matching element. So meaning you want to combine few components together. So when if you want to combine and replace it with the equivalent component, so you need to calculate the particular value that you want to. So let's say you have a resistor, so 100 ohm, and you have a capacitor, so let's say 10 farad. So if you want to find the equivalent circuit, then you need to join it together. In terms of mathematically, you need to join it together in order to find the proper resistance that you want to. Uh, so maybe if you combine, initially it was 100 ohm. So once you combine, you replace it with 150 ohm of a resistance. So it give a equivalent power. So that's what they say here. So stray source and load resistance can be absorbed into the impedance matching network by proper placement of matching element. So matching element, it can be a capacitor. Okay, a capacitor, we can place it in a parallel, or we can have an inductor, so we place it in a series. So by using this, so we can perform absorption, so absorption to the component. So instead of why absorption is very important, because it can simplify the complex circuit. So instead of you using three component, so you combine it together and make it one component. So that is what we call absorb. Absorb means in Bahasa Melayu we call as serap. So all become one, three become one. So that is what absorption method is about. Okay, so example of absorption method. So use absorption method to match the source and load impedance at 100 megahertz. So you have a 100 ohm. So you have an imaginary part J 126 ohm. Then you have a matching network. So this side you have a capacitor. So minus J 795.8 ohm, and also 1 kilo ohm of load resistor. Okay, so what we need to do first, we ignore. Okay, so we ignore the stray reactants first, then solve the matching network. Okay, so here this part you throw first, and this part you throw first, then you will get like this. Okay, so 100 ohm and also 1 kilo ohm. So and you attach it into matching network. Okay, so uh, first we ignore first. Okay, so we ignore, then we try to find out, so what are the values that is needed in the matching network, then we replace it accordingly. Okay, so one example. Okay, so the same question. So 100 ohm, so you have impedance, you have a capacitor, and also load resistance of 1000 ohm. So you do calculation similar like earlier. So once you calculate, so you get this formula or these answers. Okay, these answers you are replacing into the circuit. So we can see, so the new element value L prime and also C prime are given by, so L prime is L minus L stray. Okay, so earlier we saw, so the total number is of excess is 477. Okay, so here we divide it into two. So 200, so first part is 200, second part is 277. So you combine together, so you get 477. Okay, so what you do, you create a new element, so you make it like into two parts. Okay, and capacitor also you do the same. Okay, so capacitor earlier 4.8 picofarad. Okay, then we divide it into two. Okay, one is 2.8 pico, and one more is 2 picofarad. So combined together, you will get 4.8. Okay, then this is 1 kilo ohm. Okay, so you try to complete this kind of circuit. So then these are the some of the steps. Okay, so ignore the stray reactance of source and load. So note that inductors will be placed in a series with three inductors. So you try to create the three inductors. So how to create the three inductors? So by minus from the actual L. Okay, so actual value. So L is this. So you minus a three. So you can get this value. Okay, so S3 here is 200. So here is 2 picofarad. Okay, note the topology to be used. Okay, topology is based on the four quadrant I showed you earlier. So you determine which topology, then you calculate the Q, the quality factor. Okay, and absorb the stray reactance with series and parallel combination. So you can. So after you solve this, okay, so you can combine this together, and you can combine this together. So in order to form two components. Here you have 6 components. So 1, 2, 3, 4, 5, 6. So you will make it into 2 components. Okay, this will be combined as one, and these 3 will be combined as one. Okay, so absorb the 3 reactants using series and parallel combination. Okay, so that's the first method, absorption method. Then we have a resonance method. Okay, so what is a resonance method? If the three source and load reactants can be resonated with equal and opposite reactants at the frequency of interest. So you select one frequency, and let's say you are giving here 50 ohm of signal. So you are sending a equal and opposite reactants. So minus 50 in order to cancel it out. Okay, so when you cancel it out and you enter into matching network, so all the losses will be cancelled out. Okay, and only the message will be retained. Okay, so example, the resonance method. So use resonance method to design a matching network that will match a source resistance of 50 ohm. So you have a source resistance 50 ohm to a capacity load of 75. Okay, so the frequency is 75 megahertz. The matching network should block DC. So the question already say it must block the DC current. So you need to, okay, go back to show. So if you want it to block, so you need to determine between these two. So you check whether RS is bigger than RL or RS smaller than RL. Then you can determine the arrangement. Okay, so example, resonance method. So resonance shunt 40 picofarad with shunt inductor parallel resonance. Okay, so you replace this in the formula earlier. So you can get the value equals to 112.6 nano Henry. Okay, so match the 50 ohm source resistance with the 600 ohm load resistance. Okay, so here the load resistance is 600. So you calculate. Okay, so QS equals to QP. So this is from based on the previous question, previous equation. So 600 divided by 50 minus 1. So you get the quality factor to be 3.32. Okay, so excess, so you just replace, so you will get all these values. Okay, so next what you do, proceed with L network matching. Use capacitor or series element for DC block. So refer back to the quadrant. Okay, and inductor for shunt element. Okay, so capacitor you put in series. Okay, capacitor you put in series, and the inductor in shunt. So you have two lines of capacitance. So combining the two inductors in parallel. So here you have two inductors. So you combine it to make it. So you are using voltage division. So you make it 87. So you already reduced. So slowly you need to reduce until it become a series. Okay, so you can continue to do until you get just a single circuit for impedance matching. Okay, so some notes on the L network. Okay, L network matching. So major limitation with two elements matching network is restriction on the circuit Q. So we have two elements. Okay, only have two elements here. So restriction on the circuit quality factor. Okay, so that's one of the limitation because it depends. The quality factor is depends on this part. Okay, RS and RL determine circuit quality. Okay, please hold on. Okay, so QS and QP determines the sorry, RS and RL determines the circuit quality, because circuit quality is depends on these values. So it's strongly heavily depending on RP and also please apologize because here is mentioned here as RP. So please all this RP you replace it with RL to avoid confusion. Okay, so designers does not have the freedom to specify circuit quality, because when you are developing antenna or a circuit, so this part of Q, because Q is depending on this circuit. So this circuit usually will be developed by someone else, some other production line. Okay, so but when you are designing an antenna, so antenna you need to match with your PCB. Okay, so all these will be in your PCB, right? Printed circuit board. So usually the antenna will come with the electronics as well as the antenna. So this part will be in the PCB. Okay, so when you have that part on the PCB, the designer of the antenna, they don't have the freedom to specify the circuit Q. So let's say they want quality with 100, 100 a value of 100, but the circuit that they get so is like not really good. So it only can give a Q of maximum 10. So the designer does not have the freedom to specify. So it will become like a problem lah for them. So they need to like find another way to reduce the expectation to 10. From 100 become 10. Uh, so it will cause some problem. So becoming an issue for IQ, eye quality. So when you want to use a narrow band and even for low quality application, because when your antenna and also the circuit are not really matching, so it will be hard to have a impedance matching. So meaning it will produce some kind of losses, which we can avoid. Okay, so to address this issue of quality flexibility, so designer must specify practical circuit Q required. So before the production prepare the circuit, so the designer of the antenna must tell them, I want the circuit to have this kind of value of Q. So they make arrangement. So they will change the resistance value, capacitor value, inductance value, so that it can give a suitable or practical Q that they wanted, and can achieve larger Q than what can be achieved using LNet. So we can try to work on a larger Q, because L network. So usually it can produce IQ, but we will not produce it. We will try to depend on the other networks. But if we can achieve a larger Q than what we can achieve with L network, then it will be much better. Okay. So in order to do this, so we can utilize pi network and also T network, so which we will discuss tomorrow. Okay. So any questions? Any questions for today's? So not a lot of calculations are involved, but certain questions later I will give in the tutorial. So what I try to do, so I will try to finish up my chapters first, then I will try to give a tutorial session. Okay. So I hope you all can do some kind like own reading or exercise to whatever questions are given. So I try to give some tutorial questions, maybe in 1 or 2 weeks time. Okay, for you to practice for your final exam. Okay, so any other questions before we finish? Okay, so please hold on.
No, sir.